Good morning, everyone. Sorry for the delay. Welcome once again to the JKMRC Friday Seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would just like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country, and we recognize their valuable contributions to Australian and global society. So it's my great pleasure to welcome today Mahdiyeh Razeghi. Maddie holds a bachelor's and a master's degree in geomatics and completed her PhD in satellite geodesy in 2020 at Newcastle University, focusing on Australian water resources studies. She later joined the Research School of Earth Science at the Australian National University, ANU, for a joint project with Geoscience Australia evaluating the Great Artesian Basin groundwater. Subsequently, Maddie served as a research fellow at ANU's Institute of Water Futures, introducing a novel approach using remote sensing to study aquifer change and underground water resources. Currently, Maddie is a lecturer at the University of Southern Queensland, School of Surveying and Built Environment. And today, the title of the talk is Remote Sensing Insights, Monitoring Water Resources and Environmental Changes with Applications in Mining Rehabilitation and Groundwater Assessment. Please join me in welcoming Maddie.
Thank you. So this is working, right? Yeah, cool. Hello, everyone. My name is Maddie. Thanks for attending my talk. It's my pleasure to be here. Today, I'm going to talk about the remote sensing insights, especially with the application that we can have in mining, and especially those related to water resources. I'm going to mention some of the environmental interactions that we have with mining. Obviously, this is not all of that, but these are the ones that I think I can contribute. I would like to have this talk as a very interactive discussion. I would really appreciate if that at the end of the talk, you help me, shout on me, any comments, any discussion, any recommendation, any question, helping me to figure out more about how can I help mining studies, especially because I'm new to Queensland and mining is a heart of our economy and financial resources in this state. I would like to help, I would like to be involved, and I'm going to explain to you the tools and methods that I use, and I would appreciate at the end to have interactive discussion over how we can have that in mining studies. So we're going to talk about the subsidence, soil moisture changes in terms of content distribution due to mining, groundwater impacts, surface water changes, and drought. And I want to mention also here that I don't mean that mining impacts on environmental changes. I am very actually curious about the other way around, how, for example, environmental changes, climate changes are impacting mining too, right? I'm very curious in both ways, not only one way of mining impacts. Let's start with surface deformation in mining. We know how mining changes the ground deformation and makes huge subsidences, and it is affect both terrain and building, and sometimes even making earthquakes. The form of the deformation depends on the mining method and whether it is underground, open cast. For example, in underground mining, the cause of the deformation is water relation, displacement of the rock mass. It can be both continuous and discontinuous deformation, and size and form of the deformation depends on the exploitation depth, size of the site, and post-mining void, and a lot of factors that I'm sure you guys know much better than me. I'm new to mining, but you guys been here for a long time. If you look at the figures, for example, you see that we have this fissures zone due to the mining, and those zones are making a huge vertical subsidence along with the horizontal movement, and the question is whether we can see accurately how much we have this vertical subsidence and horizontal movement using remote sensing. The second is the impact on soil moisture. The subsidence that we have due to mining alerts topsoil physiochemical properties because we're stretching, we're squeezing, and we're fracturing the ground deformation, and then it changes the soil permeability, which later we will have different hydraulic properties. We will have this sinking basin, as you see in the figures, due to mining, which changes which increases only even the soil water infiltration velocity, because we will have a lot of cracks, right? It makes sense. Due to these cracks, we will have more infiltration and change in the infiltration. And it's not only soil, it will ended up having different vegetation communities and ecosystem in the region. The next is the impact on groundwater. As I told you, there is no question that we have a lot of impacts from mining on environmental changes, especially groundwater. That figure from OGIA in 2018 shows how Surat Basin groundwater level changes before and after coal seam gas mining. But I'm just gonna repeat myself in this case that I'm curious in both sides, right? Like how mining is impacting groundwater and how an area with over extracted groundwater already is impacting mining operation. And I would like to know if you have any insight over that at the end of the discussion. Surface water impacts. This is something that I was not aware. For example, I had a talk at the Center for Water, Claire's group within SMI, and thanks to them, I realized that there are some mines that are making ponded area as they go further, and there will be a lot of little water bodies. For example, in this mine, we're going to have more than 70 ponded area at the end over the Earth's surface, and the question is how we're changing the whole ecosystem in this region with having this ponded area. The last but not least is the drought. Water scarcity affects everything, right? But there is a huge risk of having water scarcity for mining operation. There were mines which had to be shut down because of consistent drought. It wasn't because it was misunderstood. It was because the drought was consistent and not perfectly anticipated. For example, Cadia, coal and copper, I'm hoping that the pronunciation is right, in Australia was very close to be shut down in 2007 due to a millennium drought, which shows how much drought can impact the mining operation. And as I told you, I'm curious in both ways of impacts. This is, for example, one of them. The environmental interactions are inevitable, right? They're there. We just need to deal with that. We need to mitigate the environmental impacts and have sustainable resource extraction. And for that, we need a reliable monitoring system. I believe an integration of various remote sensing tools and techniques in various spatial and temporal resolution can help us to have a reliable monitoring system. What is remote sensing? You all know about that. It's data acquisition from the distance. The sensor can be either on the satellite or aircraft. My expertise is only satellite. Detect and record reflection or emitted energy is how it functions. It provides a very global data set or localized data set, and it can help the decision makers in terms of current and future situation. The first tool is GPS, GNSS. So GPS is the American satellite constellation, and GNSS is a broader name, global navigation satellite system, which includes all of the positioning system, Russian, European, Chinese, Japanese, Indian, all of them. So when I say GPS and GNSS, I mean the broader name. Sorry for any confusion beforehand. So this amazing data set gives you 3D displacement, and this 3D displacement can be a combination of all of the available driving resources that made that displacement. It can be solid earth, it can be surface mass loading due to hydrology, due to atmospheric pressure, it can be plate tectonic, it can be viscoelasticity, which is for ice melting million years ago that we still have the rebound for that, and it can be groundwater changes, which is about porosity, poroelasticity. It depends on what you want from GNSS. You have to isolate the time series for your own purposes. The main application that we use is this precise positioning and looking at how the earth is responding elastically, elastic deformation. What is that? Any type of surface load, it can be hydrology, it can be atmosphere, even it can be artificial loading. We will have load and subsidence to respond to that loading. And when the load is vanishing, we will have unloading. The Earth's surface goes back because the Earth's surface is elastic. It goes back to the state which it was. This is elasticity response, right? And as a PhD student, what I did was inverting vertical displacement over Australian continent to get water water resources. For example, the blue time series, here's the water storage only from GPS time series vertical displacement over Australia. It is perfectly consistent with the other products of the water resources, but in higher temporal resolution. You can have hourly, daily data sets from GPS. It's amazing. And you can even get atmospheric pressure. In the center of Australia, we realize that we have more atmospheric pressure, and in the coast, we have more hydrology pressure. And we can see all of those elastic responses to this surface loading in Australia only using GPS vertical displacement. That was the first time to do this, and I was proud of that. It was beautiful. And then when I was at ANU as a research fellow at Institute for Water Future, my question was if I can use GNSS for groundwater this time. The top row is that elasticity that we discussed. It's larger scale, but the down one is pore-elasticity response, which is consistent with Terzaghi's principle, which says change in the pore pressure is in the opposite of change in the effective stress. What does that mean? Just look at the aquifer shape, which is first very localized. When we pump the water for any purposes, the hydraulic head drops, groundwater well, hydraulic head drops, pore pressure decreases, and aquifer is experiencing a lot of stress. And due to that stress, Earth's surface shows subsidence, and GPS observes that subsidence. And when we have recharge, like a rainfall or flooding, hydraulic head goes up, groundwater well goes up, pore pressure increases, and pore pressure increases, yes, and the aquifer is not experiencing much of a stress, and then we will have uplift as a response, and GPS record that response as an uplift. So as you can see, GPS, if we isolate it to only pore-elasticity, can detect the aquifer changes and groundwater. Using the same simple, we get that cyan time series in the down. The blue one is the original time series when you haven't isolated, but the cyan one is the pore-elasticity response recorded but not under a GPS station over Lachlan catchment in New South Wales. And the red ones are the groundwater wells, which are definitely consistent with what GPS is showing. And using them, we get the aquifer storage coefficient, which is one of the most important component in groundwater study that we get it from models, but this is from observation. And using that coefficient, we get the groundwater storage volume variation here, which is observation-based calculation based on using a lot of models. Here also you can see all of the climate events that has happened over Lachlan catchment, from the Millennium Drought to all of the La Ninas and floods that the area has experienced. This study was highlighted last year in the EOS AGU magazine because it was interesting for them to see only GNSS and only without even using any other data set can show us how the aquifer is changing and groundwater variation. But this is the study that I did last year, and that was my AGU talk in December. I'm sure that all of you guys know this area much better than me. Colombola GPS station, Dolby GPS station, and Toowoomba GPS station. I realized that in this small area, when you divide the area by the 151 longitude, you see very different pattern. Like, for example, look at this one. The blue is the GPS station responses, and the red ones are the groundwater wells. The depressurization time reported by OGIA was in 2014. For both of the data sets are showing this depressurization, right? But in the west of that longitude, you don't see any replenishment or recovery, even though we had La Nina over the area. But in the east one, around the Dolby, around the Toowoomba, for example, you see that the area started to get replenishment and recovery after 2020. Even the precipitation was a bit higher after the pressurization, but due to the compaction that we had in the west area, there was no replenishment and recovery, but in the east one, it started to get relatively a bit of replenishment. Turns out even this is also the trend of hydraulic head or groundwater wells before the depressurization, not too bad. After that, it start to get red, to decline. And then after La Nina, the east one is getting a bit of recovery, but not the west one. Turns out that the west one is very close to the mining activities area, actually plus agriculture, but the east one is relatively distant, and that's why it is getting that replenishment and recovery after the La Nina. This is another study, very good one, Southern Highland Coalfield in New South Wales, which they use GPS in both vertical and horizontal to show 3D ground deformation. As you can see, they show exactly how much the mine site was subsided up to minus 55 centimeter and how it is moving toward north horizontally, which is absolutely perfect and accurate. So GNSS is accurate, free data set. Yeah, of course, you have to buy the receiver. Can be mounted remotely, provide both vertical and horizontal displacement, and it has very high temporal resolution. It can even give you hourly data if you need that. But another application of GNSS, which is very novel, started 5 years ago, and I'm very interested in that, is GNSS IR, GNSS interferometric reflectometry. What does that mean? So far, we only use GPS or GNSS as precise positioning, right? And for that, we need to avoid any type of reflection. We just want to see the satellite directly, right? But what if we put the antenna intentionally on an area that we see the reflection and we study that reflection? This is what we're going to do with GNSS IR. We put the antenna intentionally over a water body, over soil moisture area that we're interested, over vegetation, crops, and we study that reflection that we get from that object. I'm interested personally in water levels and soil moisture application of such a simple method. I mean, it's not that simple, but the concept is simple. And I'm sure that both of them are very useful in, for example, mining activities. I told you, thanks to Claire's group, I realized about such a application that I was not aware of. These small bodies, these small water bodies that you see in this mining area needs a very accurate, easy, low maintenance sensors to check or to monitor the water level changes over these water bodies. I put my finger intentionally in that figures for you to see how the sensor is simple. That's the GNSS receiver, the chip. That's the Raspberry Pi, the mini computer that I use for data transfer and processing. And that's the GNSS antenna that we need to mount it in the way that we see the reflection from whatever reflection that you want to see. It's absolutely low cost, low maintenance, very accurate, near real time. You can have the data hourly and process it even in half a day. Very high temporal resolution, can detect different types of reflection. Even there was this study in France, and only one, I haven't seen anyone else, which uses GNSS IR for mine soil contamination, mine-induced soil contamination. I have no idea that how did they do that. I'm not, but it's absolutely interesting. I would love to work on that too. The next tool is InSAR, interferometric synthetic aperture radar. How does that work? The radar antenna continuously transmits microwaves toward the Earth's surface and records the reflected back to the antenna. Each pixel is a complex number, meaning that we have both amplitude and phase. Look, how does that work? In acquisition number 1, for example, we have A1, V1, amplitude and phase. And in the acquisition number 2, if there is any ground deformation, the radar the radar wave has to move faster or slower, depends on whether it is subsidence or uplift, right? Then we will have different phase or different amplitude for the same area. But what we are interested in terms of ground deformation is the phase difference. It is in the interferogram of only phase for the ground deformation. Amplitude has its own application, but not for the ground deformation. And then this interferogram is hugely impacted by the topography, right? Obviously, because topography is that the big changes of the surface. And then we need to remove that topography, digital elevation model, and we get the differential interferogram. You see those cycles of the spectrum here? We call these ones fringe, and they are equivalent to the half of the wavelength each. So if you want to know how many displacement you have, you just count number of fringes and multiply to the half of the wavelength that you have used, right? This is how does that work easily. I personally was interested in what happened to my hometown, Tehran. There were a lot of reports of very obvious cracks and subsidence before 2000. mid 2015 or early 2015. I took only 2 interprogram, but the whole study is available by these 2 people who are a friend of mine at GFZ. I only took 2 frame of SAR images and made interprogram August 2015 and March 2016. And you see a lot of fringes around southwest of Tehran where the airport is, which is exactly the area that people reported those displacements. And turns out the reason is over extraction of the groundwater, which is absolutely a huge risk to any industry, any urban activities, everything. These days, I'm busy to see how the InSAR can study the interaction between mining and groundwater. And as I told you, I'm repeating myself again. I'm curious in both ways, how the over-extracted area is impacting mining and how mining is impacting groundwater. And at the end, how the flow is gonna change, for example, if the displacement is happening. This is a very good study on Europe at greater region of Luxembourg. There is this famous area for subsidence, the border of Germany and France with huge mining activities. They did this study from 93. They took InSAR from 93 to 2011 to study the ground deformation. The top is vertical, the down is horizontal. Those gray area are where the mining are, and the bold area with the colors are where the subsidence is happening. As you can see, most or probably all of the deformations, both in vertical and movement in horizontal, are where the mining activities were in the border of Germany and France. And they were even confirming this result with the water level variation in the mines, which were absolutely consistent together. This is another study that I like because they use both GNSS and InSAR. So these days, people usually combine GNSS and InSAR to get the deformation over any mining site, because these 2 data sets are very accurate and they fill each other's gap and make each other better, of course. This is a very good plot showing a gradual vertical subsidence or for only even four months, like December 2018, April 2019. You see that from 0 subsidence, we ended up to 30 centimeter of subsidence in different area. Very accurately shows the gradual subsidence happening over the mine. And here you can see the comparison between the InSAR and GPS in both vertical and horizontal. So not only they are super consistent in terms of showing how the mine is changing, but also you can have a very accurate estimation of how is the vertical subsidence and how this subsidence is moving horizontally. InSAR is super accurate, completely remote, near real-time result. If you buy private images from private company, can be used for prediction. These days is very common to incorporate InSAR results for mining subsidence prediction models because it makes it more accurate and more valid. Very high spatial coverage, you have the whole frame. It can be both vertical and horizontal displacement. The last but not least tool is the Gravity Recovery and Climate Experiment GRACE satellite. GRACE measures the variation in Earth gravity field caused by mass redistribution. Let's look at this amazing animation by NASA. GRACE is this twin satellites which follow each other at 500 kilometer altitude and 200 kilometer inter-satellite distance. The position of each satellite is being measured with a very accurate GPS, and the inter-satellite distance is being measured by microwave system in micrometer accuracy. The change in the inter-satellite distance is due to the change in the mass over the Earth's surface or near the Earth's surface, and this mass variation is due to water variation. And by water, I mean the water at its all forms. It can be ice, it can be snow, it can be terrestrial water, it can be ocean. And at the end, you have this monthly mass variation, which is only due to water covered globally by GRACE. This is, for example, the 2019 data set covered by GRACE. But the challenge with GRACE is first the spatial coverage. Each grid is 300 kilometer. And then for about probably the temporal resolution, which is monthly, we can work with that monthly, that's okay. But the spatial resolution of 300 kilometer limits us in many ways, but there are ways to downscale that and still have a very accurate total water storage estimation. For example, when I was a postdoc at ANU, I assimilated GRACE total water storage into hydrology model to estimate groundwater over Great Artesian Basin for Geoscience Australia. I'm not going to go into details, but I'm just going to say that at the end, the GRACE result, the assimilated result was as accurate as the GRACE result, but in a better spatial resolution. So there are ways to downscale it perfectly. There are a lot of studies using GRACE and InSAR together to see the interaction of the mining and groundwater. One is good at groundwater estimation, GRACE, and one is good at subsidence changes in SAR. But I just found this very interesting study. This is a NASA-based international study, which was supposed to be about groundwater stress on 37 main aquifers all over the earth. From Australia, they use Canning and Great Artesian Basin, as you can see. They were not supposed to talk about mining, but they ended up talking about mining when it comes to Australia. The top one is about groundwater use, and the down one is the groundwater depletion that we get from GRACE. As you can see in Canning, there are not much of groundwater use. Even less than 1% of the area is residential area. But the groundwater depletion that we get from over that area is the third highest in this program, for example. They even check the recharge, and even the recharge millimeter per year in Canning was not bad, or even was not that different from Great Artesian Basin, but still the third highest depletion is something. So it turns out the mining activities in that area is affecting the groundwater in that sense that even though the area is not residential, even though there are not much of groundwater use, but we have this very huge compaction due to mining that shows us that groundwater depletion that GRACE calculates over that basin. This one is very interesting. I love this study. I would like to use GRACE for climate changes and climate events. I'm affiliated with Institute for Resilient Regions, and talking with them, I realized that the Great Artesian Basin future changes is in the interest of government. They want to know how the gap will go in the future. And especially because Queensland has the biggest portion when it comes to gap, right? So what I did was calibrating the total water storage, projected total water storage for the whole century by the GRACE total water storage to make it more valid, right? So those maps are showing the calibrated total water storage with GRACE for the whole century from, I don't know, 1980-ish to the end of 2100. The way that I calibrated, there is a very long story about that. It was not that easy. It's going to be published hopefully soon, and you will see the way of calibration. And then using that total water storage calibrated, I got the drought index, which shows us how much the drought is severe, how much it is frequent, what's the index of that. These are the things that we need to know about the drought in the future for the whole century. And I did that over 5 different climate scenarios. I'm sure that all of you know about the climate scenarios. I'm just going to mention here 2 of them, RCP 2.6 and RCP 6. So these are climate scenarios presented by IPCC, Intergovernmental Panel of Climate Change. Representative concentration pathway, it's all about greenhouse gas concentration. For example, 2.6 says the temperature rise is not going to be more than 2 degrees Celsius, which is very hopeful by the end of the century. But RCP6 is saying that the temperature rise will be between 3 and 4 by the end of the century, which is a bit more realistic if we are lucky, right? So I'm doing this for 5 different climate scenarios from both CMIP 6 and CMIP 5 to see how the gap is going in terms of the drought. And I'm very curious if such a thing can help mining operations for a better sustainable operation. And then next I can do a similar thing, which I haven't started, but it's easy now that I did this for the groundwater projection by the end of the century and see how the gap is going in terms of such a big change. I'm done. Thank you.
Thank you, Maddie. That was really interesting. Are there any questions for Maddie? Maybe I'll start. I assume there will be a lot of questions later on.
I'm looking for interaction discussion. So shout on me.
Yeah,
whatever you have.
They can't shout because they need to be heard on the mic, but yeah. So my question is, so you mentioned that, what did I want to ask? Well, so do mining companies actually use this data to predict like the
InSAR, yes. InSAR is being used in many countries actually.
Okay.
But it will be incorporated in the subsidence prediction model, right? The subsidence prediction model is already there. But before InSAR, there were a lot of assumptions involved and they were not that accurate. But now that we have this very accurate millimeter data set, very remote. Now we can incorporate that and having a much better model for prediction of the subsidence.
Okay, cool. And do they actually see a quantifiable improvement in whatever actions they can take?
Yeah, I've seen some studies showing that how it is changing the prediction model in terms of subsidence. Yeah.
Okay, that's cool. Yeah.
I'm Eddie. Thank you very much for the presentation. So you show a lot of the subsidence and uplift, and I think most of the time you're talking about like more porous aquifers, but you also have different ones like dissolution, fracture ones. So what do you think how much the rock that's hosting the aquifer is gonna like influence on the subsidence or uplift? How much do you think like that's important or not? Like if you have porous aquifer, that's probably more dangerous or it's gonna have more pore pressure and the other one's gonna be a little bit more stable. What's your thoughts on that?
Yeah, very good question. Actually, one of the things that I haven't started, but I was told by a colleague at Fener School in ANU to look at was looking how different types of aquifers are responding when we look at GNSS time series. I've seen that over Murrumbidgee area, New South Wales, that when we have different geology, GPS responds differently. You still see that uplift and subsidence due to pumping and recharge. But in terms of what is down there, in terms of material, sometimes we have the delay. So this lag depends on how much the rock is hosting the aquifer. So we will have sometimes, for example, with some material, more delay of the response of the subsidence, and with some we have simultaneous response.
Which one would be the simultaneous and which one would be more delayed?
Clay unconfined was very simultaneous.
Very good presentation, Maddie.
Thank you.
Yeah, it's Paul from Ogia. So yeah, I'm wondering, like you also mentioned that like 4 different remote sensing technique, they all have a limitation in terms of resolution, right? You mentioned Greece is at a few 100 kilometer scale. For InSAR, it's much better.
Yeah, sure.
But when we deal with this, because at the moment we are heavily involved in the InSAR data in threat basin. So, for example, there's a tension there. So the farmers, the landowner, they want to know something happened, let's say 10 meter, 20 meters away. So then like I'm wondering like what's the limitation based on your experience for InSAR data, how much you can go. For example, if you look through the literature, most people would say, okay, we want to use the InSAR, you have a grid soil 500 meters times 500 meters, something like that, a few hundred meters resolution. But is that possible? You can push the limit to like 10 meters by 10 meters, that kind of things.
Yeah, okay.
Yeah.
A very good, first of all, it's a very good question because we always have this challenge in terms of spatial resolution, especially when it comes to small aquifers. First of all, if you're lucky to have GNSS stations around, that GNSS station can detect up to 40 kilometers. That's my experience. 40, sometimes even 70 kilometers shows the aquifer changes perfectly. This is what I've seen in 3 different aquifers over New South Wales and 2 in Victoria. But if you don't have GNSS station around, InSAR can be combined with other types of data set to get a bit of downscaled and still be accurate. My experience is that tens of meters still InSAR is good, tens of meters, but you cannot go, for example, with 10 meters and say, oh, okay, so I want to know what is happening with InSAR in 10 meters. No, even tens of meters, you have not much accuracy, but you still have some good results to present. But yes, there are ways to combine InSAR with in-situ observation or even other satellites to get a downscaling, but it still be accurate.
So I'm intrigued by the combination with the geology, say, going over from Toowoomba out to the west. So the transition from basically a whole lot of fracture controlled, probably porosity, versus intergranular porosity as you go out into the Great Artesian Basin. So how do you actually see, or are you factoring in those different types of tectonic sort of rock groups, I suppose, and their relative porosities into this? I mean, it would be really cool to see that, some of that stuff on tectonic maps and porosity maps and things like that of the host rocks.
Okay, are your question, okay, is about, so your question, I'm guessing that it's about how we can see tectonic changes from GNSS, right?
No, more how the nature of the rock groups, the big tectonic, or the map of the geology basically changes some of this interpretation, because as you go out into the Great Artesian Basin, the nature of the porosity changes a huge amount. And I'm just wondering whether you can, how much of that you can see in the data.
Okay. Okay. About the Earth's surface elastic response, we don't see much of the changes because we still have that elasticity of the Earth's surface, that the load is here and then the load is getting unload and it's going to be vanished. But the amplitude of these changes varies, right? The amplitude varies, depends on the geology. About the poroelasticity is something that I mentioned to Daniel, is that different types of material underground is making this lag for the response. So the harder is the material, we have later response from the GNSS, right? Okay, so in terms of poroelasticity, the lag, in terms of elasticity, amplitude. This is what I have experienced so far, and I hope that I'm right.
The online people right here.
To set up the direct correction to porosity. But as Maddie mentioned, actually this is a very useful tool for you to figure out this specific storage. But if you have specific storage in some location, right? But sure, there's also challenge because like sometimes if you have multiple aquifers, like what we are dealing with for InSAR basin, different core measures, they are superimposed with each other, that's a trouble. But in many locations, actually, you only have one good aquifer to pump water from. In that situation, you can figure out the specific storage. But once you have the specific storage, you can try to correlate that to porosity that comes in.
Thank you.
Yeah.
Cheers, Kristy, and thanks, Riley. So you've obviously talked about satellite, and you mentioned briefly aerial platforms. What do you see the opportunities for drone applications, and particularly for drones being able to do things that the other platforms aren't necessarily doing? And obviously, there's a spatial resolution gain there, but I'd love to hear your thoughts on other ways that they can contribute.
I don't have much knowledge about drone. Sorry about that. I'm mostly satellite person. But of course, when you use drone, you can have any spatial resolution as you want, right? The drone is moving over whatever area that you want. So you can have a coverage of whatever area that you want once you have the drone flying over that. But I'm so sorry, I don't have much knowledge about drone.
Let's talk afterwards then, because I think we can maybe help each other.
Oh, that's great. Thank you. Good to know.
I think, so just one point, actually, I probably thought the same thing. So when you look at race that you mentioned, the spatial resolution, so it's like, I was thinking like, is this something that can be done with drones as well? and then flying them over the area and then get that distance measurement.
With gravity. Yes.
Or the distance from the Earth.
We already have airborne gravity, which is very famous and very useful, but very expensive.
Yeah,
Yes.
but that could be something like the same technique that is used with gray satellite now. You do it with the
Oh, I
drone
see what you mean.
and then get that.
Yeah.
2 drones following that. I don't know, it just came to my mind.
That would be
Inter drone distance changes due to the. It's interesting. Go for it. It's a new idea. You're a good entrepreneur.
So there is some 2 online questions from Human Hari. So first one is, what is your idea about using remote sensing layers for detecting karstic water resources?
Sorry, what is
your idea?
What's the word before water resources?
Using remote sensing layers for detecting karstic.
Karstic.
Yeah.
What is it?
Karstic's like the dissolution aquifers with, like, for example, carbonates.
Yeah. Oh yeah. Sorry. I have zero knowledge about it. I'm so sorry.
All right. So the second one is, how much reliable the visual data delivered from drone for detecting trend of landslide zones in residential,
again.
yeah, and non-residential areas.
As I mentioned, I use the sensors over satellite.
Yeah, apparently there's a lot of people interested in using drones.
Yeah, of course, yeah. But no, I'm not a drone person, and I'm very scared because it is being recorded. If it wasn't recorded, I would shout some. But it's been recorded, I'm not gonna respond. Yeah, I'm not gonna make any evidence.
Okay.
She has a
Well,
question.
sorry.
Thanks for the talk. It was really interesting. I was just wondering whether this type of technology has been used for the detection of earthquakes and
Oh, yeah.
tsunamis, like
Oh, yeah.
because of the water
Yeah, exactly.
movement that's sort of before a tsunami, you know, like.
Yeah. There is an alert system in Japan. Yeah, based on GNSS and based on InSAR, obviously, because so this layer down there are more softer than what we see on the top, right? And you can have this response very earlier, right? And then it can be detected both by InSAR and GNSS, and it can be an alert system which they're using in some countries. And actually, my master degree was about using GNSS for stress analysis plus earthquake, that we have a lot of earthquake in Iran. And I showed how GNSS can detect that and easily show the magnitude and the changes vertically and horizontally. Yes?
Any other questions?
Maybe just another question. So you show like all those droughts and how like environment can change the aquifers to its dense uplift. Do you see mining companies like bringing this kind of study or something for like feasibility or kind of predictability of the soil behavior or like aquifers for the future? Do you see that happening?
Actually, that is my question from this community, that whether we can incorporate this study, for example, in terms of aquifer changing, and ask the mining companies whether they are considering that for their mining. You know, I'm new to mining. I'm not even beginner. I arrived in Brisbane 8 months ago, so that's why I decided to think about having mining in my application. But I've seen some studies in US incorporating InSAR data set in terms of aquifer into the mining operation. So what they see with those studies is both subsidence and how the aquifer is changing, and then comparing those results with what is happening in the mining, both before and after, which shows how much, for example, their prediction was accurate based on their models that they use for both subsidence and water resources down there. Yeah, my question is whether we can do similar stuff in Australia. That's actually my question.
Yeah, I think it's be even interesting to, when you're like mapping out all this data from the aquifers, even to how you're gonna plan your mine, where you're gonna put like a TSF, where you're gonna put this or that.
That is my question. That when I say I'm not only looking for mining impacts, On, for example, groundwater, I'm actually curious on the other way too, that how groundwater is impacting mining. And I would like to know if they're doing anything in mining companies regarding that, because I'm not that much aware of what is going on in terms of.
Me neither, but maybe a good opportunity there.
Yeah, should be. I don't know. You help me.
Steve.
Not a drone question, right? It's been recorded, otherwise I would talk a lot.
We can have a discussion on that afterwards.
Hi.
Just a comment on that last question from you. Yeah, a really interesting area to look at in terms of groundwater and mining is actually anything in the Arctic.
I would love that, yeah.
Because in the Arctic, we have the extra problem of permafrost melting. And so that's having all sorts of really negative impacts. So super interesting, yeah.
Yeah, I mean, it's not drone.
Oh, yeah.
Now Mohsen is gonna exclude me saying that use 2 drones with the laser between them. You don't need many. This is how Mohsen helps me.
Yeah.
Oh, yeah.
Yeah, so just for the record, Mohsen is, so there's another piece of innovation that we've been involved in developing, which is digital twin technology.
Oh, yeah.
And visualizing massive amounts of data. We can do it for the whole of Australia, could do it probably for the whole of the world. And we could easily put these, anything that's spatial can go in. So we could easily integrate this in there.
I'm teaching digital twin next trimester for master students. So that would help.
I mean, one suggestion in terms of mine and mine closure planning would be to go to something that is in the coal fields that's now being closed and work hard on collecting the data for the closure process that we're actually observing. And from that set of data, you would then be able to use it for as a predictive tool. And so if I was going to suggest a project that's out in the coal basins, for example, then going to look at a closure process and then following the subsidence and following the evolution of the groundwater and how that changes with that closure process, and then being able to apply that to the end of mine life sort of stuff would be something really worth. The other project you could look at is you could always talk to Rio Tinto, who just took over from ERA closing Ranger, which of course is up in a different basin and different watershed, and it would be a good type example for what's going on there.
And are they open to give me any type of data set?
Well, there's a huge amount going on with that at the moment, and it's a phenomenally expensive process. But they would probably be happy to get any help they can with that process.
Okay. Thank you. Very good ideas.
Great. Thank you, everyone, for your contributions and your questions. Let's thank Maddie again for an interesting talk. So then next week we have Lulit Ekubasion from JKMRC talking about one of her studies. So hope to see you all there.